Ora si registrerà la conferenza.
Okay, so the monitoring activities has been carried out in Veneto, in the north of Italy, and here in the map you can see the contamination source in blue, and also the sampling area. Sampling area was painted in 3 different colors, representing 3 different PFAS pressure, level of PFAS pressure. Indeed, matching the results of the biomonitoring study to that of drinking water, the local authority divided the contamination area in 3 zones with different health impact. Here you can see the red area, so the area of max exposure, the yellow area, the area of precaution, and then the green area, that is an area not directly impacted. In these 9 representative sampling sites have been selected, and a reference site located north of the impacted area have been also included. All sampling sites were characterized by the presence of the water body used for irrigation, agricultural soil, vegetable species, and terrestrial invertebrates. We have collected a sample of abiotic and biotic metrics, in particular irrigation, water and soil, and animals and vegetables. About vegetables, we have selected 3 kinds of cultivated crops: an epigean crops, lettuce, an hypogeal crop, onion, and extensive crop, maize. In addition, a spontaneous plant has been also included. Spontaneous plant is the Phragmites or reed grass. So from May 2018 to October 2020, the irrigation water has been collected monthly, while soil and abiotic samples have been collected twice a year during the harvest season. Here I have reported the sampling sites, so the number of samples that our colleagues from the University of Padua have collected. This monitor program aimed to reach 3 different goals: to study the variability of PFAS concentration in irrigation water, to assess PFAS contamination in agricultural soil, and to evaluate PFAS uptake in spontaneous and cultivated plants. All samples have been analyzed by methods that were redefined and optimized at the beginning of the project. Indeed, the analytical procedures were developed to optimize the detection of short-chain PFAS due to their high potential to be translocated and bioaccumulated in plants than long-chain congeners. Abiotic samples have been analyzed by HARPAS, so by Environmental Agency of Veneto, while biotic samples have been analyzed by CNR. Briefly, the PFAS determination in abiotic samples has been performed by PFAS extraction with methanol and water, and PFAS quantification by LCMS. In biotic samples, PFAS were determined by were extracted by ultrasonic extraction with acetonitrile and water, and quantified by LPNT. In particular, about animals extract, these samples were injected by TFC, so by turbulent fluorochromatography, that has been avoided for vegetable sample because we wanted to improve the recovery of short-chain compounds, so the recovery of early eluting compounds. These analytical procedures were showed during a previous webinar that whose record is now available on the project website, while the determination of PFAS in plants, the validation of this method was recently published. About plants, you can notice that the samples were divided into its fraction, so into roots, stem, and also leaves, and in case of mice, also in corn cob and corn kernels. And this step allowed us to study the partition of PFAS in the different fractions of the plant. Okay, now about the result. Here you can see the levels of PFAS concentration that we have found in the samples. PFAS concentration are expressed as the sum of the congeners, and to calculate the concentration in wood plants, the level found in each fraction was added considering the biomass of each fraction. So, about irrigation water, the concentration ranged from the limit of detection to 5 micrograms per liter. And here you can see that some events of higher contamination has been recorded. About soil, concentration ranged from limit of detection to 27 nanograms per gram. And finally, about the plant, you can see that we have found concentration ranged from limit of detection to 10 nanograms per gram of wet weight. To understand if these areas were contaminated by PFAS, a comparison to reference sites have been done. Here you can see that increase of PFAS concentration from reference site to red area has been observed. In particular, you can see this increase in water. But this increase was not confirmed by statistical test. Here you can see the results from ANOVA test. In particular, you can see that the concentration in red area were significantly higher than those in the other areas from waters and soil. This means that green and yellow area were not more contaminated by PFAS than the reference area. Thanks to the data set, we have observed also the levels of PFAS in irrigation water, and we have observed that this level have an higher variability during the year. Here I have reported the trend recorded in 3 sites, and in particular you can see that the levels ranged to the limit of detection to 600 nanograms per liter. So a very high variability that can be explained by the fact that the channels of irrigation take water from different sources according to irrigation request and season. A short mark about biotic sample. As you can see, only reed grass has been considered because this organism is the only organism always present in all sample sites. Reed grass is a common aquatic vegetal species often used for phytodecoration in artificial wetland. Based on ANOVA test, you can see that the 3 areas are not more contaminated by PFAS than the reference area. Until now, I have presented the result considering the area classified by the different level of PFAS pressure. Here you can see the concentration of PFAS recorded in each sample site. In particular, you can see that sample sites belonging to the same area showed a very different concentration. This is very evident regarding water, irrigation water, but also in soil. In particular, you can see, for example, that in this sample site, that I cannot see the map, but in this sample size, the level recorded were very very lower. And this is displayed because at this point, the irrigation water take water from river. About animals, you can see that only in one sampling site we have recorded high PFAS levels. In this case, the contamination in animals was mainly done by PFOA. Here you can see the difference between the level recorded in edible plants and the level recorded in reed grass. First of all, we can see that the concentration recorded in edible plants never exceeded 2 nanogram per gram of wet weight. And that these concentration were every time lower than concentration recorded in reed grass. Another important result is that in reed grass, concentration better reflect the classification based on the PFAS pressure. Now about PFAS composition. As you know, PFAS is a group of heterogeneous compounds with different chemical physical properties. In particular, the behavior of these compounds is driven by the length of their chain. Based on this, you can see that in irrigation water, the contamination is was mainly done by short-chain PFAS. So PFAS more water soluble. In case of soil, the contamination in soil was dominated by long-chain PFAS, so more lipophilic substances. Based on this, we have investigated a possible correlation between the total organic carbon and PFAS concentration, in particular of the mainly present PFAS that were PFOA and PFOS. But as you can see in the graph, no correlation between the TOC and PFAS concentration was found. A completely different situation has been observed in plants. Indeed, in this case, the composition of vegetal contamination was affected by the sampling site. In fact, you can see that in a plant taken in the green area, the main compound were the long-chain compound, so compounds released in the past and accumulated in the soil. On the contrary, in the red areas, in plants taken from the red areas, the most present PFAS were compounds of recent origin, were short-chain compounds. Now, about PFAS in the different fraction of the plant. You can see that the majority of PFAS in red grass were found in leaves. On the contrary, the majority of PFAS in maize were found in leaves, but also in corn cob. About PFAS composition, another important result has been observed. Indeed, root stem of reed grass were mainly contaminated by long-chain PFAS, while reed grass leaves were mainly polluted by short-chain PFAS. On the contrary, in maize, root and stem were mainly polluted by short-chain PFAS, while leaves were mainly polluted by long-chain PFAS. Another important result is about corn cob and corn kernel. Indeed, you can see that the opposite situation has been observed, and you can see that in corn cob the majority of PFAS were the short-chain PFAS, while in corn kernel, the majority of PFAS were the long-chain PFAS. Okay, now I'm going to conclude and I'm going to summarize the most important results that we have found. We have found that in irrigation water, PFAS concentration are characterized by a very high variability. In addition, events of higher contamination were occasionally recorded. About soil, we have found that level of PFAS recorded in soil reflected the area contamination based on different level of PFAS. Indeed, the highest concentration were found in a sample from the red areas. About plants, we have found that the contamination level was similar in the three areas. The contamination level was similar, but the contamination composition was very different. Indeed, in the green area, the plants from the green area were mainly polluted by long-chain compounds released in the past, while short-chain chemicals of more recent origin were dominating residual samples taken in the red area. Again, about plants, we have observed that in edible plants, the concentration recorded were lower than those measured in spontaneous species, and this concentration never exceeded 2 nanograms per gram. About Phragmites, we have noticed that this plant is a good model organism in monitoring of contamination due to its ability to accumulate PFAS. As you will heard in the next presentation, this plant can be used also for remediation in artificial wetland. And thank you for your attention.
Thank you, Claudia. And I think that maybe I ask you if you have some question, you can open your microphone and ask a question if you have. If anyone, or write in the chat. I want to stress that the situation that we saw into this monitoring is that the irrigation water is driven, of course, the concentration in irrigation water network channel is driven by the discharge. That's you have also to underline that the company is now closed. So in the last year we passed from 2018, when there is still activity of the fluorochemical plant, to 2019-20, where the activity of the plant was closed. But nevertheless, there are still a lot of PFAS into the network, because also there is the use of also for groundwater to for example, for industrial activity, and they discharge into the river. So there is a recycling of this PFAS also from groundwater that is characterized by all the groundwaters that are characterized by all P4 as main compounds, because they are the first production from 70 to 2010 was P4 for polyfluorotetraethylene production. Why in the more recent year, from 2010, maybe they moved they changed the production from long chain, from P4 to PFBS and PFBA from the C4 compound. That also we have these two. That's why we think that the soil that is impacted by accumulate more accumulable compounds, right? And also we see that the soil was more impacted by by P4 when they are outside the core of the pollution event. but nevertheless, we reach also 5,000 micrograms per liter for total PFAS in the irrigation water, but the agricultural product are exposed only to a small part of this irrigation water. Why? Because there are also other, there is many sources of water that the network channel use. They are, of course, the request, the demand, the water demand from agricultural period are different, and also the meteorological are different, and conditions are different. So there is the request for water from one source and another can be different, and this position, of course, you cannot model, of course, the plant uptake as in an hydroponic situation that you have a constant irrigation water exposition, and irrigation water was the only way to get water from the plants. Though I think that field experiments, we are working in a real field without no artificial. We take the condition that we found that the agricultural, we don't put any constraint to. We look at the situation, the real field situation, and we see that, of course, even if the irrigation water is really impacted, the soil also and the wood plants are not so. Of course, 2 nanograms, 4 nanograms, 4 grams are the maximum levels measured in the edible water, and that's okay. If you use TDI from EFSA, maybe they can represent a risk, but we have to compare them to the background real concentration everywhere. That I see that. Sorry, Claudia, I try to contextualize your data on the situation. I see that there are a lot of questions in the chat. Good. Okay, Laura Fazzini asked what were the detection limits for the soil. Have you data, Claudia Ferrari from ARPAV, about the detection limit of soil?
0.5 nanogram per gram.
0.5 for a total for each. For each. Okay, thank you. Is there Nike Moloney says, if there are any form of PFAS more dangerous than other? We are looking only to the perfluorinated acid, perfluorocarboxylate and perfluorosulfonate. So we don't have measured the precursor. That's a clear uncertainty, added possibility to have. So, and between about the dangerous, of course, we have to distinguish between legacy C8 long chain compound that are more accumulable, and then we found also into the biomonitoring into the blood of the people living there. Of course, people are exposed more to drinking water than to agricultural product, but in that the red, the green and yellow and red areas are defined by the blood and drinking water data. So it's an artificial division that Regione Veneto divided the area for giving the assistance, the sanitary assistance program to the people, and define the different exposition. So if you get, of course, short chain compound that are more present into the leaf, large leaf plants are less accumulating to the blood, but we don't know if they have the same mode of action. This is a discussion about that. Though we can, the risk of this compound are different, but they are, for example, more mobile. So we can think that they are not accumulating the trophic chain, but are mobile, and we are exposed the same to short chain, but without accumulating them. And Laurent Almaric from BRGM say to be sure to understand correct, is it correct that your result, sum of PFAS, are obtained by TFC analysis, not by calculating the sum of individual PFAS measure? No, sorry, there is a misunderstanding, because TFC is not total fluoride. Okay, but TFC is turbulent flow chromatography, though the sum of PFAS are obtained by calculating the sum of individual PFAS measured by LC-MS. TFC is only the purification system we call online purification system that we call turbulent flow chromatography. So the sum of PFAS are the sum of, we don't apply any integrated measurement of total fluorine or total oxidable compounds. That's okay. We are only the sum of 12 perfluorinated carboxylic acid and sulfonic acid. Concerning remediation, which plants show high PFAS uptake and could be considered for PFAS removal? Okay, about concerning remediation, we stop and we talk about that after the presentation of Marco Bonato, the next presentation, and we come back to you. Why the short chain PFAS found in the plants in red area are believed to be more recent compared to long chain PFAS or the green area? Not in the plants, but I think we would like to. Claudia, tell me.
No, it's correct. It's about
the soil, not in the plant.
No,
yes.
no, in
the soil. Yes, there is a misunderstanding. Come back to the soil. Okay.
It's refer of this result, I think.
Ah, no, sorry. Yes. Why we are you to be more recent? Okay, green area are not impacted directly by recent irrigation water, and we think that irrigation water are rather unimpacted, of course, as a background concentration, of course, some nanogram for liters. And we see that there is it's only some experimental observation, and we think that the air transport maybe from and the accumulation in the soil of long chain compound is a source, can be a source of this compound for plants. If you think that if you have mobile compounds, short chain are mobile, they don't accumulate in the soil, and they rapidly are goes through the vadose zone to the groundwater. Why the long chain PFAS are accumulating in the soil and stay there, and can be a source, of course, for plants, because for roots, because this is wool plants. Yes, of course, we included also roots in this analysis. And in this case, our hypothesis is that when you are in the red path, you are exposed to irrigation water where the long chain prevail, and while when you are in the not impacted by irrigation water, the source for plants could be soil contamination, that is a background contamination, maybe from air, from waste, recycle from dump field. That's it should be studied, of course. That's our hypothesis. I don't know if we have better to study the thermometer. One critical point to study how these compounds contaminate all the environmental components, and how they spread everywhere. That's a clear point. Air, the waste cycle, or not. That's a point that we would like to stress, to study better the next future. Of course, there are no other questions. I can pass the floor to Marco Bonato from University of Padua, that can show two presentations. The first one was on the sorry, Marco, I was looking for you to the list, and Okay.
Okay.
You can share, Marco, you can share the video. Marco Bonato works at the University of Padua, and he was the people who also organize and coordinate all the monitoring studies and also the study on the phytoremediation. Thank you, Marco, and go.
Thank you, Stefano. And now you can see very well the presentation. Or is okay?
We see and we heard you well.
Perfect. First of all, I would like to really thank you, Stefano, for his consideration, because I'm not a professor. Thank you again, Stefano, but I'm just only a postdoc from the University of Padua, of the Department of Biology. Thank you again, Stefano. Maybe in the future. Okay, we go very quickly, talking about the possible, my presentation is about the phytodepuration as a nature-based solution for PFAS mitigation. This particular action, sub-action, is about the action B3 in the project, is about the technological innovation and development, and it faces and they meet two main topics. One about the irrigation water, and the other one is about phytodepuration. These are the two sub-actions that are involved in this particular topics, like irrigation water and phytodepuration, that, as I mentioned above. And these are the two sub-actions. The first one was a realization of a pilot plant to test if the phytodepuration could be a valuable tool for depuration or mitigate the concentration of PFAS in irrigation water. Then we will try to upscale our pilot plant to real size area within the project area. I think that you know very well what is phytodepuration. There are hundreds of possible definitions of phytodepuration. This is just one, the more easy I have found on the web on different papers. This is one from Professor Borin of Agriculture Department, and phytodepuration is just as a natural treatment technique that reproduce natural purification processes that normally are done in a natural environment, and that is possible to perform also in controlled environment. To set up our pilot phytodepuration system, we was granted to make in Dall'Ava Vivaio, which is a seller of different kind of plants, like flower plants and so on, and is completely inserted in the red area near Lonigo. So this phytodepuration pilot wetland system is well set in B3.1, our sub-action. This is just to say images regarding the our depuration plants, and I will just briefly summarize how is the function of this pilot plant. This is just a technical scheme, just to show you how it functions. First of all, there is a polluted pit in a red circle where we catch the water from a pollutant underground. There is a tank of storage where the water polluted is stored. Then, by a pumping system, there is a pump that will pump water directly within the water depuration system, and there is another pump that flows out in the outlet. All this system is automatic and remote controlled by different kind of sensors. In the main tank, where are our phytodepuration, we have planted 200 Phragmites australis, the common reed, over 3 different layers of gravel, from the big gravel in the bottom, then medium gravel, and the fine gravel in the upper part. This is the growing of our phytodepuration system. As you can see in the left pictures, the system has a solar panel, so is completely detached from a power supply. And on the right side, you can see a timer because the main problem was to recreate the natural situation of a wetland area. As you know, in a natural wetland area, normally the water flows in a constant way, within the area. So it was not possible to perform these continuous flows because it was too spend too much energy from power supply. So we decided to have point pumping timing, to have a different pumping timing to pump water within the system, and consequently the flowing out of the system. All the system has a real-time control for remote system. As you can see, this is where the phytodeprecation system is located. These are different parameters that we normally measure inside the system. Obviously, it's not possible to measure the PFAS. We measure the water level within the system, and we can also, as a control about the pumping system, to have a slow speed or increase the speed of the water flowing. The most important is to set the flowing and the residence time of the water within 5 or 7 days in order to have the best performance for the common reed to make the absorption of PFAS within the water. Just to show you very, very briefly some results about our phytodeprecation test. Here in the pictures above, you can see the hydraulic balance of the system. Because what we have a measure of the system, we measure the water that come inside, the quantity of water, the volume of water that go inside the system, the volume of water that flows outside the system, in order to have a volume balance, an hydraulic balance between the water in and the water out. You can see in the table, in the first part of the table, there was a volume loss regarding the water that flows outside. This is obvious because means that the water, the plant made his job. And we have performed a test for 180 days during the growing season of the common reed. We have seen that the mean PFAS load during the inlet, during the day, is about 1,400,000 nanogram per liters, and the outlet is obviously quite less. And the PFAS, so the PFAS absorbed daily by our system is 169 nanograms each day. So for one season of growing, the system is about to storage within the wetland system, the pilot wetland system, 30 milligrams each year. We have to consider that this is a 3 cubic meter pilot wetland system. So it's a very small system, but it works very well. And it has a mean phytodeprecation capacity of 12%. So it means that every 100 nanograms of PFAS that enters within the system is able each day to store 12 nanograms. It could be obviously very, very, very tiny quantity related to the chemical filtering for drinking water. But we have to notice that this is the first idea of possible activity to mitigate the PFAS concentration in irrigation water. We have seen that the system works very well. So we try to upscale our system to have a real size wetland area. This is the second part, the second sub-action, the B3.3, is a demonstration of full-scale plant. And just to test if the phytodeprecation could be a possible mitigation strategy for PFAS concentration. We have tried this in 3 different wetland areas, in the 3 different zones. So the Monastero wetland, the Monselice wetland, and the Cadimezzo wetland. As you can see in the map, these are related in 3 different parts of the project area, in 3 different zones: red area for the Monastero, yellow area for Monselice, and green area for Cadimezzo. All these areas are managed by the Land Reclamation Consortium Adige Euganeo that give us all the help related to logistics and other stuff in order to completely use this wetland area and wetland system in order to perform our testing. The first activity related to set the residence time of water flows within the areas were not performed because all these areas are very well studied by the University of Padova, by the research group of the Department of Industrial Engineering, coordinated by Professor Luca Palmeri, one of the team of the University of Padua that works on the LIFE16 project. So we have all the information related to the water flows. So I just go very, very quickly regarding to the results. As you can see, obviously, these are real size areas. So the water capacity of flowing within the area are huge related to the water capacity, obviously, of a 3 cubic meter area. The whole areas cover like more than 20 hectares of phytodepurration capacity. As you can see, the water volume, the water flowing inside and outside the system are really huge, more than 5 million cubic meters each year that could be treated within the area. So the PFAS, the total PFAS concentration, the total PFAS load that could be treated from the volume of water that pass through this wetland system is more than 500 grams. And the incredible stuff related to this system, the natural system, is about the capacity of the system to storage PFAS within the wetland area, which is more than 500 grams per liter, the 500 grams each year. So a mean capacity abatement of over 50% of what comes inside the system. This is a really big result for the project. And for the future perspective for phytoremediation, we can say that yes, this is a first possible mitigation for irrigation water, for PFAS, for mitigate the PFAS concentration within the irrigation water. I have to remember again, no treatment are nowadays applied for mitigate the PFAS concentration in irrigation water. So this could be a possible mitigate technique that could be used for perform this activity. It could be applied not only on wetland area as the classic wetland area like Cadimezzo or other stuff, but also to the whole small channels, nets that are within the project area. Because all these channels are full of common reed that could be treated like a small wetland area. I have to remember that Veneto Region has one of the biggest capacity of phytodepurration in Italy, with over 300 wetland area coordinated and managed by 11 land reclamation consortium. Obviously, the problem is all the PFAS that are storage absorbed by the system, not only by the wetland system, but also the whole system, so the sediments and so on, need new policy for mowing the common reed and obviously for the waste management related to the common reed mowing. But we think that this could be a real, a new possible way to mitigate the PFAS concentration, also because it's a method that is practically without cost, because the wetland system has no cost of management, except for particular artificial area that has pumping station that pump water inside the system, and obviously that flows outside with pumping and other stuff. But these are just costs that are within the Land Reclamation Consortium activity. So this could be a valuable tool in order to mitigate the PFAS in the irrigation water. I would like to thank you for your attention to my presentation, which was very briefly, but I would like to have time maybe to have some discussion or other stuff. These are the research team of University of Padua that involve 3 different departments: the Department of Biology, the Department of Industrial Engineering, and the Inter-University Research Center of Public Economics related to the cost for action activity within the project. So thank you again for your attention, and if you have a question, I'm just here. Stefano, I just give you the throne.
Thank you. Okay, we recovered the question before from Marco Prete. I think no, from Andreas, who asked you which kind of plants, I think, which kind of plant show PFAS uptake could be considered PFAS removal in soil. Have you tested different plants, or only why you choose the fragmites?
Okay, we have not tested other different macrophytes because the first we would like to use we have used the common reed because this is the most ubiquitous plants that is possible to find in Veneto region and also in all the other Italy for phytoremediation, and related to some data that we have gathered from how to say gray literature, like other theses and so on. We have seen that also for other different kind of pollutant, the common reed is the plants that has the highest capacity of absorption related to different kind of pollutant, to heavy metals, to nutrients, to pesticides, and so on. But obviously we are open to different kind of experimentation. There is a Tifa ulva or other kinds of plants that could be possible to use.
But in your artificial wetland, you plant these fragmites, or are they spontaneous?
No. We have planted by ourselves the fragmites in order to have to recreate what is the normal to say environment that is possible to find in the normal natural fit of the wetland system.
Okay, I have a question, a comment or question by Maximilian Lutke. Impressive result with close to 60% of capture of the PFAS within the wetland. Any comments on the ultimate fate of the captured PFAS? Will it be at risk of being accumulated in animal eating from the vegetation and being forwarded high in the food chain to more mobile species? I can say something maybe.
Yeah, if you want to.
Yes, I think, I don't know. I don't think that fragmites could be used for confirm for breeding animals. Do you confirm that?
Yes, for sure.
And those are not particularly eaten. We don't think the problem is to waste them, to cut and waste. That's another. Yes.
No, if I can just do Stefano after I add some stuff.
But the other problem, for example, for maize, we see the similar situation, and also maize could be represent a minimum risk of transmission of accumulated PFAS into the trophic chain as breeding animals or cows and so on. But of course, one of the key issue that we have to understand that the plants, the uptake of the EPIGL part of the plants is better for the short chain compounds that are not accumulable. For that reason, the risk of transmission to the called biomagnification, something like that, is very low for short chain compounds. While the compound that like PFOA or PFOS, especially PFOS, that are of course important into that can exert a clear biomagnification activity into the trophic chain, are mainly blocked into the soil or into the roots of the plants. That's a clear, I think, a clear result from all the plant study. And Marcia Albiero asks us, the intervention on phytodepuration is really interesting. Thank you for Mark.
Thank you.
However, we cannot think without considering a complete remediation of the contaminated site above a refill flap. Okay, yes, that
Stefano, sorry, I just to add one stuff about what you have said before regarding
yes,
the fragmitas.
Sorry for
No, don't worry. We have to consider that maybe we can see better in the next presentation related to experimentation, that the common reed is lives normally within the water, and that have no bias related by soils that could stop the flowing of the PFAS. That's why normally the results are so impressive, because there is a direct connection between water matrices and the fragmitas. This is this is the way. Okay.
No, it's correct consideration. About have you some hints about the hints about the use of this as bioremediation in site, or do you think there is any possibility to use that or not?
To use this for
site contaminated, for example, the chemical plant.
This is difficult because we have to, if I have understand well the question, we have to build a completely new wetland system in a contaminated site. If I have understand well the question.
Yes, maybe they feed on water, not on soil, so you need another. I don't think. Massimo, hello Massimo, caller from CNR, Massimo Zacchini. Did you try to evaluate the contribution of the different components of the wetland, plant, sediment, biofilm in removing PFAS?
We have tried to consider it for the different part of the plants for sure. Related to sediments and other stuff that are within the system, we have to make a more accurate, more analysis that needs, how to say, different kind of also permission to make the sediments analysis, because you know very well that looking for the sediments, we have to ask for particular permission, because there are some policy related to the possible risk related to the sediments and so on. But this is a real good point for future analysis.
3 questions about, I summarized them, about the problem of moving and waste management. Okay, what are the main obstacles today in terms of waste management? What happens with the reeds after it is moved? And but concerning moving and managing the waste, wouldn't it be expensive? Because to me it seems only option is to burn the waste, and we need concentration more 1000 degree at 1000 degree. What about that?
Right question, and center the points for sure. There are not obstacles in terms of waste management. How to say, obstacle is not an obstacle, but it's just to change the policy. We have to add some policy related to how we have to treat the mowing of a channels or a wetland system where we have certified that there is a PFAS in the water. This is a step, and this is I think is a very quick solution. The other question related to the cost. What I have to say that the system of phytoremediation is at practically net no cost. The waste management is another part, and is okay. This is a cost, is a really cost, but we think that a possible solution could be to take this waste, the mowing, and convert it to particular plants that could burn this without create other kind of problem, and use the surplus of energy that are produced by this burning in order to cover the cost of transport. This is a possible idea to cover the cost of transport the mowing from a wetland area to the sites where the mowing will be burned. This was a possible idea and a suggestion that we have done, that we tried to make to the policymaker, to the waste management direction of different plans. But we have also, obviously, we have to test it. Maybe there could be maybe another project to to try this.
Okay,
If this
next life.
yes, the next life.
Okay,
in all way.
We are a little late, but
Yeah,
no problem,
sorry.
because we have time to discuss. We would like to discuss, and I think that I suggest you to pass to the other presentation.
Yes.
The other presentation is about the laboratory and greenhouse study on the uptake of PFAS by Radicchio.
Yes, red chicory. Okay, you see, I think very well.
Yes.
I'm here on behalf of Professor Carlo Nicoletto. He's a real professor, not like me. And Professor Carlo Nicoletto is very busy for lessons, and so it was not possible for him to attend. So I'm here to show the results about our experimentation of the LIFE project team with Professor Nicoletto related to an exposition of an edible plant, the red chicory, the radicchio, in a controlled environment. Just to briefly summarize some stuff, we have chosen red chicory, the radicchio, because it is a widespread cultivation in Veneto, one of the most cultivated in Veneto, obviously less than crops, normal crops, like because for these particular soils, needed of soils that yeah, it has. And we have tried to understand the different mechanics of PFAS uptake in red chicory with two different experiments. One with the soil, so in normal in pot, in different pot, in several pots, and the one in hydroponic, so without soil. And just to see how are the different mechanics of the PFAS uptake in these particular crops. Okay, we start with the hydroponic system. I will try to explain the best as I can related to the research topic of Professor Nicoletto. We have chosen the particular variety of red chicory, the Chioggia one, because it was the one of the most cultivated in the south in the whole project area. We have used an experimental hydroponic system with a nutrient solution, with a fixed nutrient solution, and was spiked with with 9 different kind of PFAS, and we have measured the evapotranspiration of the plants, and clean water was added weekly to account the lost nutrient solution. The nutrient solution concentration were analyzed for PFAS concentration in the beginning and obviously in the end of the experiment. Grant to our partner in the specific ARPAV for the water, and after for the soil analysis. These are the experiment plant. This is a pictures related to hydroponic cultivation. So this is a box mainly with the floating system, and the water, the plants are directly connected with the water, or polluted water or controlled water without obviously pollution. These are just very briefly the different concentration of PFAS that we measure in the roots during the treatment, and the concentration of PFAS, different kind of concentration of PFAS in the shoots. We have just measured 2 different compartments, the roots and the shoots. I have to remember that the shoots are the edible part, the one that normally we purchase in the supermarket. So during the exposition, we have noticed immediately some physiological changes due to exposure to PFAS. As you can see, this is a control system where you can see the perfect shoots, perfect roots, and no problem related to the growth. This is obviously the roots and the shoots of the plants related to the highest concentration of PFAS that we have used. So what we have seen that first is physiological changes are also, as you can see here, there is a inverse correlation between nominal concentration in the solution and the total plant biomass, as you can see in the graphs. These are other experiments that was performed by the laboratory of Professor Carlo Nicoletto, not directly related to our project. Professor Carlo Nicoletto see which is the concentration of PFAS in different other kind of cultivation, not only the red chicory, the radicchio, but also in lettuce, cabbage, zucchini, and tomatoes. As these are the hydroponic systems, and this is the transpiration factor. So you can see there are quite differentiation between the hydroponic and non-hydroponic system. What is the conclusion related to the floating system test? We have seen that the long chain PFAS mainly accumulate in the crop roots. More than 65% and 9% of their mass remained in the roots in the study. Why the short chain PFAS, particularly C3 and C4, are readily transferred to the shoots. Compared to carboxylide sulfonates, PFAS with the same per-follicle chain length absorb more strongly to the root. And the RCF for the long chain PFAS have similar values among the crops, while the short chain PFAS absorption to roots is more crop kind dependent. Generally, the transpiration factor for PFAS are low, and in the case of addiction of the red chicory, show only very small decrease between the C6 and C9. Quite opposed to the most of the other crops where it increased, as was reported in the project. Now we would like to check what happened during the project, during the experiment, but in the pot, using the soil. We use the same kind of variety of Chioggia red chicory, was grown in a greenhouse for a period of 38 days in a hydroponic system, the late before, and 80 days for the soil experiment. This is because the soil is a natural bias for flowing the water and consequently for flowing the pollution. So normally the plants in hydroponic solution grow very quickly grow quicker related to the soil plants. The soil experiment was performed in 12 different treatments with spiked irrigation water, spiked soil, and different kind of combination, as you can see in the soil experiment scheme. The same kind of perfluoroalkyl acid were used, the PFAS, and we tried to calculate the KD and KOD from this test for use for other kind of for modeling. These are the different kind of concentration of PFAS that we have used for the irrigation, and this is the concentration also of different soil. So we have polluted, we have spiked to both the soil and the water. So here there is clean soil and clean water as our control, and this is the most spiked for related to soil and water, and this is the other different kind of pollution. These are the results related to the concentration in water and concentration in the soil from the roots concentration and the shoots concentration. There is a correlation, very interesting to see, of roots concentration factor with the soil to water coefficient, the KDs, for treatment with pre-contaminated soil. This is quite interesting. So just to summarize very quickly, very sorry for going very fast, but I try to accelerate in order to to recuperate some delay that we have done before. There is a clear differences that can be seen the pattern of PFAS accumulation from the experiment in hydroponic solution and the one in the soil solution. The transfer of PFAS from roots to leaves in hydroponic decreases with the PFAS change length, while it's mostly constant for the red chicory that is growing in the soil. The most important stuff to see is the soil is making a difference, not only reducing the bioavailability of PFAS in the water, but also for the root development. Much larger roots system was developed in soil with greater surface. This is related to the nature of the roots. They are searching for water, so they have to spread within the soil. Then this is not happening in hydroponic solution, in hydroponic experiment, where the whole roots is at complete submerged in the water. KD and KODs are very low for the short chain PFAS. Also very important to notice is that there are different transpiration volumes that are measured for plants from soil experiment and related to hydroponic. All the results that are showed here are now are possible to see in two papers that we have already published. One related to the soil experiment and the other one in the hydroponic. And the other one for the hydroponic test. I have forgot to say before, related to the phytodepuration system, that we are writing a paper related to our results for the phytodepuration system, both pilot phytodepuration and the real size area, in order to collect and explain all the results that we are collected related to the phytodepuration. Thank you for your attention. I'm sorry if I go very, very quick for this presentation. If there are questions, I try to answer.
Okay, thank you, Marco. Sorry for hurried you, but of course all results are already published, so you can, if you are interested, you can read with accurately into the paper, and also there are large supplementary materials. I don't see any at the moment, any chat, though I give the floor to Greet van Gestel, our host from the OVAM, the soil agency of the Flanders, that should share with us the experience in the soil monitoring and assessment in the Flanders. Thank you, Greet, for having accepted to give a presentation in our webinars, and I give you the role of speaker, and you can share the video. We see the presentation, and okay, also in the okay, present perfect.
So good morning.
Thank you, great.
Yeah, thank you, Stefano, for the introduction and also for the invitation to speak here. So my name is Greet van Gestel. I work for the OVAM, which is the Flemish regional authority responsible for the management of material and waste, and also for the management of contaminated sites. So I'm very honored to tell you something more about our soil policy on PFAS. So I will tell here something about how to deal with the legacy of PFAS in the soil water system. Here a short overview of my talk. So first I will start with an introduction, so setting the scenery for the legislation and the practice you're working in. And then as a kind of prelude, I will tell you more about how we got started. And then the core of my presentation has three parts. First, I will say something about the guidelines we have just published. Then I will say something about threshold values, These are the soil remediation standards, also background values, and then there are also criteria for the use of excavated soil. The third part is then about how to deal with different PFAS compounds. I will end then with the outlook towards the future and some research needs, and add also a kind of coda or extra on international collaboration in the Emerald Soil Network. So first introduction. So as most other European countries, Flanders has also a legislation on the management of contaminated sites. This is the Flemish Soil Decree and Implementation Order Variable. One of the key elements of this legislation is the obligation to do a soil investigation on land where risk activities are taking place or have taken place. And this needs to be done periodically or upon transfer of the land. And in the legislation, a list is provided, a list of risk activities for which this research is needed. When the soil investigation indicates that the soil is contaminated, then remediation is needed. And this needs to be done by the operator or the owner according to the polluter-pays principle. So the operator or the owner will ask a soil expert to perform a soil investigation. The soil expert has to follow guidelines in which he stated how and when he needs to sample and which substances needs to be analyzed, and also what kind of risk assessment he needs to perform, and so forth and so on. A second key element of our legislation is the regulation on excavated soil. So this is a kind of tracing system to avoid the reuse of contaminated excavated soil in an improper way. So, and also here we have guidelines on when and how to sample, and also which substances should be analyzed, and also when a technical report is needed. So this whole system is working very well, but the focus is on well-known contaminants such as the heavy metals, mineral oil, BTEX, chlorinated solvents, and PAHs. And then came PFAS. So, and this with a lot of questions and uncertainties for policymakers, also for soil experts, but also for problem owners. For us as authorities, it gave a lot of problems because we didn't know how to proceed, because we had to take decisions on issues of which we know very little. So what did we do to get started? So in 2016, we started with an exploratory measuring campaign on PFAS to find out a global, do a global risk assessment for Flanders. First, we started with an inventory of risk activities. So 24 sites were selected using the OVAM database and other information. Among these sites were firefighting training grounds, but also sites where fire incidents took place. We included also sites with textile, paper industry, also paint industry, and galvanic industry was included. Also a water treatment plant and a waste dump was included. And for all these sites, soil and groundwater was analyzed for 21 different components. What are our conclusions? So first, for the concentrations in the soil, they ranged from 0 to 900 micrograms per kilograms. And this is for the sum of PFAS. For the concentration in groundwater, they ranged from 0 to 2000 micrograms per liter, and again for the sum of PFAS. The highest concentrations were found on the firefighting training grounds. So I have to note here that this activity is not included in the list, in the standard list, which is provided in the legislation to do an investigation. The highest concentrations were found for PFOS and PFOA, also for PFAS and for 62 FTS. So I'm not going further in this detail in this research, because you can read it on our website. So there is a report which is available in English. So from this study, we concluded that we have to implement PFAS in our legislation. So that's why we published guidelines. What do these guidelines say? So first, it's stated when PFAS should be considered as a suspected substance and should be analyzed when a soil investigation needs to be carried out, or when a technical report needs to be delivered for soil excavation. To that end, a list has been included in the guidelines describing the activities with a high or limited risk of PFAS contamination in soil and groundwater. And then for those risk activities with a high risk for PFAS contamination, then PFAS must be included when one performs a soil investigation, and needs also to be included in the technical report for excavated soil. Those sites are the PFAS production sites, also the PFAS processing industry, for example, the galvanic industry, and also sites where firefighting foam was used. For example, those where firefighting incidents, when there were fire incidents, and also the firefighting training camps. And also a checklist for sampling was included to make sure that there is no cross-contamination. Also, the analytical method is provided, and these guidelines, they needs to be followed for all the reports that were delivered after the date of 1 September 2020. So when we ask to measure PFAS in soil and groundwater, we also need standards to assess those measured values against. So that brings me to the second part of my talk, namely the setting of soil standards for PFAS and PFOA. First, a short intermezzo on the overview of soil standards that we are using in Flanders. So we have 3 types of soil standards. We have standards for soil in situ, we have also standards for excavated soil, and we have standards for material that is added to the soil, such as soil improving agent and fertilizers. For the soil in situ, we have background values. Those correspond to normal levels in unpolluted sites and unpolluted soils. And for metals, they are set to the 90th percentile of measured values. For organics, they are usually equal to the detection limits, unless there is a background, and then also the 90th percentile is used. Soil remediation standards correspond to a level. When this is exceeded, this can cause a serious effect for humans and for the ecosystem. So we derive soil remediation standards for 5 different land use types. So there is nature and agriculture, there's residence, recreation area, or industry. The standards for nature and agriculture are set at the same level. And then there is also the target values. They serve as the goal for the remediation of new soil contamination, and they are somewhere in between the background values and the lowest soil remediation standard. We have also threshold values for excavated soil, so the 2 types. So the values for free use of excavated soil, they are set equal to the target values. And then we have also values for construction purposes. They are derived taking into account leaching of the thing and also various receptors with the maximum level of corresponding to the soil remediation standard of the land use type industry. The values, the threshold values used for excavated soil are equal for those in sediments. So we have a bit of an overview of how those different values are connected. The criteria for soil improving agents and fertilizers are a little bit apart, because they also expressed as concentrations in the fertilizer, and they are derived making sure that no new soil contamination can result from applying them to soil. What we can do now to develop soil criteria for PFAS. So in Flanders, the general rule that for parameters without standards in the regulations, the criteria needs to be proposed by the accredited soil experts. But because for PFAS, it's quite a difficult task, so we started to do it ourselves. So we derived criteria for excavated soil, because this was most urgently needed, or because the lack of criteria leads to uncertainty and also to stagnation of construction works, which is very costly. So we provided criteria for the free use of excavated soil and also for construction purposes. These are provisional criteria, and it is the responsibility of the soil expert to apply them in a safe way. Now, at the moment, we are now changing those values. I will come back to that later. We also asked the VITO to derive soil remediation criteria First for PFOS and PFOA, because those are the substances we have the most data for. Soil remediation criteria are derived, first calculating criteria based on human tox and criteria based on ecotox, and then the lowest value is retained as a soil remediation criterion. For the human tox-based criterion, we'll be using the transfer and exposure model as risk. And then for the ecotox-based values, we have used the same values that were calculated by RIVM in the Netherlands. The results of this work you can read behind the link. The report is also translated in English. The transfer and exposure model as risk, which is also used in Walloon and also in Brussels, this model compares the exposure by different exposure routes to toxicological criteria. The uptake of PFAS by plants is taking into account for two land use types, namely for agriculture and for residents. And this is done by using bioconcentration factors from literature. So also again, if you want to know more about this, you can go to the report that I just mentioned. These are the results for PFAS, for PFOS. So you see here the different land use types, then the values for the based on human tox and the ones on ecotox, and then the lowest value of those two is retained as a soil remediation criterion. We have not, you do not see here criteria for the land use type nature agriculture, because the value we obtained was very low, and there were indications that there might be background concentrations of PFAS in soil. I'll come back to this later. Then also, what's also important to note here is that the human tox-based values, that they are based on a calculation using the tolerable daily intake of 20 nanogram per kilogram body weight per day, which was published by the US EPA in 2016. So because at the time of when these calculations were done, the European Food Safety Agency had only published provisional values. So that's why the US EPA values were used. And it's interesting to mention that the value we obtained for the soil remediation value for current water of 120 nanogram per liter, which is calculated by this straightforward formula, that this value is in the same order of magnitude as the EU quality standard for drinking water of 0.1 microgram per liter. Then results for PFOA, again, the same land use types and values for human tox, values for ecotox, and the lowest value, which is retained as the soil remediation value for PFOA in soil. Also here we obtained a soil remediation value for current water of 120 nanograms per liter. This is based on the same TDI of 20 nanograms per kilogram body weight per day. It's just a coincidence as this is the same value as for PFOS. Another thing to mention here is that leaching to the current water is not taken into account to calculate these values, because in Flanders we use a separate methodology to take into account the risk of spreading. So, and then in this methodology also the risks for leaching are taken into account. These data are now used as provisional criteria, so they are stated in guidelines, not yet in the implementation order. Then we commissioned another study to derive background values for PFAS in soil in Flanders. So this was also done by Veneto. So they selected 50 unsuspected sites and they sampled the top layer from 0 to 20 centimeters and analyzed this for 40 different PFASs. What did we find? So PFOS, PFOA, and also PFBA was found in almost all samples, so above the detection limit. So for this three compounds, we could derive background values. And you can see them here. So they correspond to the 90th percentile. So we found for PFOS 1.5 micrograms per kilogram, about 1 microgram per kilogram for PFOA, and 1.25 for PFBA. And this is this can be compared to the values that are found in the Netherlands. In the Netherlands, they use a 95th percentile. So they found for PFOS 1.4 micrograms and for PFOA 1.9 micrograms per kilogram. Also to mention is maybe that in a lot of samples, about 27 out of the 50 samples, we've also found 62 FTS in above levels, above detection limits. Then these values were then used to calculate criteria for the use of excavated soil. So we have two values, as said, so free use of excavated soil, then the soil can be used without restriction, can be used everywhere. And then there's also a criterion for the use of soil in construction purposes. And here there are certain restrictions. So, for example, they must take measures to avoid leaching. And then, very shortly, something about the methodology to derive this criteria. So different scenarios are defined, taking into account the risks for leaching. So one of the scenarios is, for example, a leveling of soil, or another scenario is a landfill. And then limited values are calculated using different distribution coefficients. There are also some other boundary conditions. The value must be well above the background value and must be lower than the lowest soil remediation value. So the results you can see below, all the limit values that take into account the risks for leaching, they are below the background values. So this makes it a bit hard to determine a criteria for the value for the free use of soil. So meanwhile, we have finalized our decisions. We are about to publish them. So we found, we decided to use 3 micrograms per kilogram of soil, all for PFAS and also for PFOA. And then we have to adjust also the soil remediation value. To explain what is at stake, I show you these results. These are data that we obtained from the organizations that manage the excavated soil. So they have data on how excavated soil is used in Flanders. So about 70% of this soil can be used as free use of soil. They can be used everywhere. Then about 20% can be used as soil, but with restrictions. For example, the quality of the soil on the site which is receiving the soil is taken into account. Then there's 70% of the excavated soil used for construction purposes, and about 3% of the excavated soil is contaminated at too high a level and needs to be cleaned. And last part, how to deal with the different PFAS. So we have now soil criteria for PFAS and PFOA. But most of our standardized analytical methods, they measure a lot more PFAS compounds. They measure up to 30 to 40 PFAS, different PFASs. And we have seen in the study, in our exploratory study, that we really do find them. Of course, we would like to have data on toxicology and behavior of all the individual PFAS compounds and also to know more about their combined effects. But for the moment, we don't have this data, so we need to have a pragmatic approach to deal with those other PFASs. Meanwhile, different ways have been proposed. So, for example, we have the relative potency factors that have been proposed by RIVM. So in that case, the exposure to a mixture of PFAS is expressed as exposure to a comparable amount of PFOA. However, in their practical guidelines, they use another approach. They use either PFAS and PFOA, or they use threshold values for PFAS or PFOS, with the value for PFAS always applying to every substance without adding up. Then also Beagle proposed methodology. So they make the distinction between the perfluoroalkyl carboxyl acids and the perfluoroalkyl sulfonic acids, and then making also the sum of these substances, and also including factors based on the properties of the substances. So also this proposal was quite complex to introduce this in practice. So we are now proposing a similar methodology as the one that is used in practice in the Netherlands. So, and to conclude then, what will the future look like? So we have still a lot of research needs. You probably know those. What's about bleaching? What about the uptake in food products? How to deal with the other PFASs and their combined effects? We also want to know more information on the relative importance of the different exposure routes. So that's why we started a research project in last year in collaboration with the Department for the Environment and the Division of Health, of Environment and Health there. So we want to find out how people are exposed to PFAS. So what are the main exposure routes? Therefore, we are planning measurements in food, and especially in food that's locally produced, also in drinking water and in groundwater, in house dust, in soil, and so on. And we will perform those measurements at the residence and in the gardens of people who are participating in a human biomonitoring program, so that we can combine those two data. This kind of result is part of the Flemish PFAS action plan, and we expect results in the beginning of next year. And then the last thing we need to set up is the inventory of the firefighting training grounds, especially those ones for which no other risk activities are present. And for all this research activity, there is a lot of need of international collaboration and exchange. So that's why we started a network on international collaboration, which is called MCONSOL network, with the focus on the legacy of emerging contaminants in soil, with stakeholders from different directions. So we have stakeholders from industry, from research, we have policymakers and consultants, and also representatives of the civil society. The aims of the network are to exchange knowledge and data, and also to set up collaborations and to raise awareness. So if you're interested, you can please join the network, and you can do that by going to the website. The website is indicated here. You can fill in a form, and then you are a member, and you also receive a newsletter. So every few months we get a newsletter. And we are planning a next meeting, which will also be an online meeting taking place on the 6th and the 7th of May of this year. And there will be a lot of talks about PFAS, but also about other emerging contaminants in soil. So, and by this, I end my presentation. I thank you for your attention. If you have any questions, so I'm happy to answer them.
Thank you, Grit, also for having been in time. And I ask people if there is no comment on the chat, but I ask people if they want to ask a question on word, they can do, and let some minutes. It's very interesting that the need for an international collaboration, because soil are not intended as something that close into a nation. Okay, Jan Martin asks you, is the background soil studies published or not?
Yeah, Bill, it's about to appear on our website. However, the documents are still in Dutch, but Vito has performed a study. They are working on a publication. So, but maybe they will be presented. The results will be also presented on the ENSO meeting. But if you really want to know more about it, you can send me an email as well.
Thank you. And yes, I don't see any other question. We can, I have only some final remarks. And yes, on the today, yes, it's important that consider that the PFAS for the one of the lessons of the LIFE16 project, that PFAS doesn't move only on water, but also on air, maybe also with the waste, for example. There is a cycle of PFAS that impact every environmental compartment, and also a single significant point sources can impact large areas with a lot of way that need to be better investigated. And also plants, of course, can be impacted by PFAS, can uptake PFAS, even if the soil could be an effective buffer for accumulating more, for storing more accumulable substances that can be released slower during the time. And also the soil trophic chain from invertebrates to mammals and also both needs to be better studied, because most of the studies till now was devoted to the aquatic chain. And also about soil, also the presentation of grid show us that there is the need to search for background concentration, and also to look for PFAS in the agricultural products. And also it's very important that the background concentration should be linked to the real threshold, because you cannot put any soil threshold or standards if you don't know this kind of background concentration. And why there is this background concentration? Maybe also a component comes from the atmospheric transport, especially from landfill, maybe from the normal use, the waste recycling, and also the waste, the wasting of our products. And also we need to derive harmonized standards for soils at EU levels. Okay, what we need, that there is no a soil legislation for soil. Common in Europe, there is no directive, for example, on soil, and also it must enforce all the network activity on soil, such as the EMCO soil, because the background concentration are related to background exposure levels for humans, and that we need to know this kind of background exposure to understand also our human biomonitoring data, because there are a lot of efforts in the, for example, in the HP4 biomonitoring program, but if you don't know the background exposure levels, you cannot interpret in many cases the human biomonitoring studies. And also there is a need to improve the green infrastructure, and maybe wetland can be one of the part of this green infrastructure in Europe. And yes, this is my final remarks, and also I thank all of you for your participation. I will remember that all recordings, will be available on YouTube channel, and also we available the recordings and the presentation are available on LIFE16 project website. And thank you all for your participation. This is the last meeting of the WIS webinar series, and thank you for great participation, active participation. Thank you to you all, and see you on the next meeting and next conference and so on. And we are all open for collaboration and for discussing, for sharing, disseminating, because LIFE projects are projects that are, as a main action, is the dissemination of the project and the transfer of our result to other people, other countries, other situations. Thank you for all. Bye, and see you.
Thank you. Bye to everyone.
Thank you.